All right, this is, I think it's day 12, but then we did the, I don't know if you want to put 12. I guess I'll put 13. I think this is the 13th time that we've seen each other, but we had the TOK for day 12, I guess. So I guess I'll put 13. Change up the notes already. AAHL, we're doing 213. This is, I'm pretty sure, an HL only topic, which is why you get such a big number. You know, we're kind of skipping on a little bit, but this is one of those things where we have to spend the day learning it, and the SL classes just kind of gets to move on. Like I said, today's lesson is rationals. Does anybody know what a rational number is? So the whole numbers have zeros, and the natural numbers are the numbers that don't have zeros, and then your integers have negatives. What is a rational? What is an irrational number? Can you think of an example of an irrational number? Pi. And what makes pi so weird? It goes on and on and on, never repeats, and blah, blah, blah. It's a crazy decimal. And because it's a crazy decimal, have you guys ever seen the fraction for pi? You have? That's crazy, Devin, because the whole point of an irrational number is that it cannot be made into a fraction. And so a rational number is a number that can be made into a fraction. It includes all the 0.5s, and it includes all the 0.33333, because that can be made into a fraction. And so when we're talking about rational functions, we're going to be talking about functions that can be made. It's like polynomial functions that are fractions. So your polynomial function might look something like x squared. Let's make a big fraction. Let's give a nice f of x here. X squared minus 5x minus 14 and x squared plus 4x plus 4. That's a nice rational function. It's a fraction. X is on the top, X is on the bottom. Particularly the X's on the bottom are causing problems. The X's on the bottoms might be 0. The X's on the bottoms are gonna, cause a possible divide by 0 major error. And we're gonna have to find a whole bunch of different things when it comes to this. And so basically, this first bit is gonna be just making a giant list of what do you need to find and where do you find it. And some of these will be super obvious and we might know for sure. Some of these may be less so. So I guess first up is the x-intercept. Where can you find the x-intercept? If you're tasked with this, I lock you in the room, I say no Desmos, no calculator, how are you gonna find the x-intercept? Plug 0 for y, which is over here, which is totally fine, but there's an easier way to say it. You're definitely on the right track. So if we plug 0 for y and then we go to solve it, what would the very next step be? Multiply by the bottom to the other side, which would be on the right track to finding the value of x, but that's like our big goal. And what would happen if we multiplied all of this to the other side and this side is already 0? It just becomes 0. So what happens to the bottom? Who cares? So the x-intercept is top equals 0. Because the bottom is just gonna get multiplied over there to 0 anyways. So we don't really care. So if you're tasked, I need you to find me the x-intercepts, look at the top and set it equal to 0. Okay? How can you find the y-intercept? The x equals 0. Is there some kind of shortcut to doing all this? Basically, the only numbers that will survive are the numbers without x. But that's not really a shortcut. So I think you're 100% right? We can just say x equals 0. I don't think there's a more elegant way to write that. But that is a really easy process. That's the y-intercept, right? All that stuff with x's is 0. It would be negative 7/2, negative 3.5. Cool. Let's go to the x-intercept, the y-intercept. We've talked about setting the top equal to 0. What happens if we set the bottom equal to 0? What does that help us find? Nice, and very, very specifically, the vertical asymptote. I'm just going to put VA because we've learned this all before, and maybe I'm lazy on a Monday, so be it. Okay? Now, what about the horizontal asymptote? Do we know how to find the horizontal asymptote? Yes, so the horizontal asymptote is one I'm gonna put a star next to. We've already talked a little bit about horizontal asymptote, or maybe that was calculus, maybe I'm just getting backwards, but horizontal asymptote, there's a couple different things that could happen, okay? First of all, for the horizontal asymptote, you're gonna need to compare the degrees. Just like Devin was saying, you're gonna want to consider those degrees. And what is the degree? Right, yes, but it's gotta be the biggest one, because you might have a polynomial that says x5, x4, x3, and you always are gonna choose the biggest exponent. And a lot of kids get mixed up on tests. It'll say something like, something like this. What is the degree of the top? And some kids will say, oh, it's 1. Because they just don't look. Sometimes they're out of order, which is just kind of like a mean teacher thing to do. But anyways, compare the degrees. If you're comparing things, well, one could be bigger or the other could be bigger. So we have a couple different options here. If the top is bigger than the bottom, if the bottom is bigger than the top, or if the top is equal to the bottom. If we're comparing them, those are our 3 different options. One's bigger, the other's bigger, they're the same. And that's gonna give you 3 different, it's kind of like a little map, 3 different outcomes. Does anybody know any of these for a horizontal asymptote? Okay, if the top is bigger than the bottom, we're gonna leave that as a blank. And what you've said is not wrong. But we're just gonna hold on to that for just a second. Any other ones? What do you got?
When it's bigger on the bottom, it's 0.
Yes, when the bottom is bigger, it is y equals 0. And very importantly, we are going with y equals because these are horizontal asymptotes. They are lines, and the y equal is how you make a horizontal line. And if the top and the bottom have the same exact degree, here you're gonna say y equals a fraction with a top number and a bottom number. And these are gonna be the leading coefficients of the top and the leading coefficients of the bottom. Now already we've just dove pretty deep in terms of vocab words I'm throwing out without explaining too much. So let me give you an example here. If it's y equals 5x squared minus 3x, and on the bottom it's 2x squared minus 10x. What would the horizontal asymptote be? So look at the degree. 2, 2. Okay, they're the same. If they're the same, leading coefficient divided by leading coefficient, which means take that fraction, it would be 5/2, which is also super easy to do. You can do that very quickly. 5/2, you can grab it. Y equals 5/2, you would just write it like that. And I do just want to point out that the leading coefficient has to come from the coefficient of that degree number of the biggest exponent. And so I'll just give you a little 2-second example here. If it was something like y equals 5x cubed minus 2x squared, 5x squared minus 10x cubed, what is the horizontal asymptote of this line? Nice job. Very good job, right? Compare the degrees. 3, 3. Then, okay, they're the same. Grab the leading coefficient. Now, this time they're not the most forward ones, but they still are the ones that count. And I circled only the 10. Maybe it's more clear if I circle the negative 10. So negative 1/2 is exactly right. Very good job, Leila. Okay, so let's go back to where Devin wasn't wrong, but I did that classic math teacher thing of, you're not wrong, but... If the top is bigger than the bottom, you do not have a horizontal asymptote. He's right. And I think I even heard him say again that you are going to have and I'm going to go with the word oblique, O-B-L-I-Q-U-E, which is the same thing as a slant asymptote. Have we ever heard or worked with slant asymptotes before? Slant asymptotes, a little ugly. Not anybody's favorite thing in the world. And so that's something we're going to end up doing today. Well, we're doing rationals, but we're also going to be working with some oblique asymptotes. The good news is, mathematically, it's not all that crazy, but it's just a process that's different from a lot of things. So if we've done vertical asymptotes, horizontal asymptotes, and we even had to mention obliques, I think up next is we should talk about the oblique asymptote. Well, the oblique asymptote is not a vertical line. That would be a vertical asymptote. Or a horizontal line. That would be a horizontal asymptote, which means it's a diagonal line, which means it's just a regular line. So your oblique asymptote is going to be of the form y equals mx plus b, because it's just going to be some sort of angled sloped line, just like a regular old line. But where it comes from is you just do the actual division, okay? This looks, rationals look like a division problem. And when you're trying to find that oblique asymptote, you just do the division. Now, for our oblique asymptote, we already saw if the bottom is bigger than the top, the answer is going to be 0. And that makes sense because if your bottom tries to divide into the top, but the bottom's bigger, it's not going to work, right? So, for example, something like 3/5. How many sets of 5 do we have? 0. We don't even have a set of 5. We've got 3, and it's a portion of some, but we do not have the extra. And if we say, oh, do the division, and we have 5 out of 5, well, okay, it's 1. That's easy to do. It's only when we have a bigger degree on the top that the oblique asymptote actually comes into play, because we have some extra, basically. So only, that's the worst y ever, only if top bigger than bottom. Of course, I'm talking about the degree there. If you want to make a note on your paper that I'm talking about the degree. And then you're just going to do division. Now the problem is polynomial division is nobody's favorite thing. And polynomial division is just kind of a convoluted mess. Now we're going to spend, quite a few problems going over polynomial division, but we'll get there in a second because there's more things that we want to know about rationals than just the asymptotes and the intercepts. What about wholes? Do we know where wholes come from? We kind of mentioned this very briefly. We did like a jump ahead to limits for like 10 minutes one day. Actually, probably like 20 minutes, but what's up? Oh. Yeah, basically wholes happen when you have a Mayday vertical asymptote and a way to get rid of that asymptote, okay? A hole is like an insane crisis that you barely dodged. So a hole is basically when factor reduces. So if we just make an equation here and we just want to put x minus 5, x minus 5. That's the easiest thing that has a hole, okay? We have a red alert insane problem. If x equals 5, we're all going to die because we're going to divide by 0. But at the same time, you can kind of reduce those fractions. And so crisis averted, sort of, okay? What this does is your graph, this one would kind of reduce to y equals 1. So this graph would kind of look like this. At that 5, there's just going to be a little hiccup, a little gap where there kind of was a crisis, but the crisis was kind of averted. Okay, and so that's what a hole is. Anytime things simplify out, you're going to get a hole. On one hand, holes are nice because basically we're able to take a whole exponent and remove it from our graph. The more x's we have, the more complicated our graph is going to be. And so when we start to remove these, it's going to get easier and easier. Now there is one thing that really sucks about holes. The thing that really sucks about holes is that you need to find the y value. This is something that you may have not had to do in your math analysis or algebra 2 class. I didn't teach you those classes, so I'm not sure what your teacher required of you, but you may have not had to do this. So let me give you another example just really quick. Let's say that we have y equals x minus 2, x minus 2, x plus 1. Okay? Let's list the vertical asymptotes. Where are we in huge trouble? Everything's going to fall apart. It's two places. X equals 2 and x equals negative 1. But this x equals 2 is actually able to be kind of crisis averted a little bit because we also have this minus 2 here. So we can kind of get rid of those. And you know what? Actually, there's only one vertical asymptote for this question. It's there. Now, if we're asked to list the hole would be right there where we used to have that at x equals 2. But the problem is you can't write a hole like this because this is a vertical line. And your hole is a gap, and it also has a y value to it. And so when you have this, you actually are going to have to write it like this, which means you're going to have to take this 2 and plug it back in and see what you get. Now, sometimes that's a very easy thing to do, and sometimes that is just going to give you something like -4/33 or something. So a lot of times you're going to get a fraction that's just a mess. When we plug 2 into this equation, again, oh, that's not what I meant to do. There it is. We're not going to plug it in there because that's just going to give us 0, but we're going to end up plugging it over here, and 2 plus 1 is 3. And so what's the y value of our hole? 1/3. Something that might have kind of also missed you there if you're only half paying attention. Remember, we plugged the 2 in, and it's 2 plus 1, which is 3, but that's in the denominator. That's why we go with 1/3. So again, you're going to get fractions a lot of times for those y values, which makes it kind of annoying. Okay, we are almost done talking about rationals. There are 2 more things here. That is domain and range. Now, of course, domain is talking about your x's and range is talking about your y's. Your domain and range of a polynomial function is typically your domain is going to be all real numbers because a polynomial shouldn't really have any issues, but your domain of a rational function is not guaranteed to be all real numbers. Your rational function is going to have those like mayday moments, and those mayday moments have to be excluded. And so your domain is going to be all real numbers, but then you're going to have to possibly exclude things like your vertical asymptote or your holes. Anywhere where that bottom is equal to 0, you're going to have a problem. Now your range is also going to be all real numbers, but you're going to need to exclude things as well. What do you need to exclude from your range? The horizontal asymptotes and also the holes. This is always the most missed question. Always. People say, oh, it's that, and then they just never find the y value for the hole. They just think that the hole is x equals 2, and then they leave it off the range. They always miss those points. Okay. Talked about all of these things. Let's crush into a problem here. Okay? Y equals fraction. Let's do that one that we had earlier. X squared minus 5x minus 14 over x squared plus 4x plus 4. All right, let's start listing things. What is the x-intercept? The x-intercept is when the top is equal to 0. Well, for this function, it's squares. We can probably make this look a little bit nicer. Can we get this same exact rational into factored form? That would definitely help. Maybe we have holes. We got to kind of look for those. Can we factor the top? Can we factor the bottom? I'll tell you that my SL2 kids are so bad at factoring that they just flopped on the calculus test. So if you're not very good at factoring, it's not going anywhere. We got to figure this out. Factoring. Anybody got the top factored? Nice. And the bottom? Oh, nice. So we actually do make things a lot simpler. We actually do end up with a hole there. Now, to be super, super clear, when we kind of cross it out like this, you're not actually allowed to simplify like that. Like these two functions, if we cross these out, those are two different functions. They look exactly the same, except for this bottom one has, or it's missing the hole that it should have. Whereas this one still contains that hole. This one, it forgot the place where there was that kind of problem. So we can cross it out mentally, but the function stays the same in general. Our x-intercept is going to be 7, 0, where the top is equal to 0, which is at 7. It's an intercept, so we don't really want to put x equals because that makes it look like a line. Okay. The y-intercept. Anybody got the y-intercept? -7/2. And remember, we talked about how beforehand it would be -7/2. And what about it in factored form? Same thing, -7/2, even after we've already crossed that out. So great. 0, -7/2. All right, let's go and start talking about asymptotes. Vertical asymptote. I always like to do vertical first because this is like your real mayday. Vertical asymptote, anybody got that? X equals -2. Nice job with the X equals horizontal asymptote. This is the one I put the star next to. What do you say? No. It is going to be 1. It is going to be 1. Compare your degrees. They're the same, so make a fraction of your leading coefficients. If your bottom was bigger, it would be 0. If the top was bigger, we would be going on a long exploration to find the slant asymptote. But that's not coming until the very next question. Then we'll have to struggle there. That means that the oblique might not even be mentioned. None. All right, there's no oblique asymptote. We didn't have to deal with that. We've talked about all of our different asymptotes. We talked about our intercepts. Let's talk about our hole, if we have one. In the grand scheme of math, holes would be very rare, but in the case of a math teacher building a question for you, holes aren't that rare. They're going to pop up from time to time. Where's our hole going to be? The hole comes from the crossed out portion, which is at -2 comma. Dang, we got to plug this in again. And for this question, when you go to plug in that -2, you still have a problem, right? That hole is the issue. Now, how would this look on our graph? I don't know that this would be something. Plugging it back in, it doesn't work. I don't know. We won't have a question like this. I'm trying to think if that would work on a question like this. Vertical asymptote, you would just go right through it. Well, D&E, I don't know. You plug it in, you get undefined, it still doesn't work. We should have come up with a better question when we randomly did it. Domain and range, you need to exclude all real numbers. X is not allowed to be -2, and for the range, all real numbers, Y is not allowed to be 1. I think that looks good. I hate it's got the worst keyboard sound ever on this website. All right, let's see how this looks. Fraction. It was parentheses x minus 7 parentheses x plus 2, right? And then x plus 2, x plus 2. So that's our function. Okay, I see our nice vertical asymptote is definitely going on at x equals -2. Yep, that looks like a nice asymptote. We also said that our horizontal asymptote would be y equals 1. Yep, I think that looks pretty good, right? Our asymptote should not be touching our graph. We also had that weird issue with the hole, but again, we have that asymptote there, so it just doesn't really end up existing. You're not going to have a hole on the asymptote and deal with that. Not on a vertical asymptote, that's for sure. I think that's pretty good. I mean, the domain looks, it's all the way left, it's all the way right, but it's not at -1. It's all the way down, it's all the way up, but it's not at, or actually -2. This scale's zoomed in weird. Yeah, not too bad. Graphing these holes, zeros, x-intercepts. Cool. Now let's get to the oblique stuff. Here's where I imagine few people are gonna say, okay, let's kind of go back. So the oblique, also known as the slanted, but again, math teachers kind of like to use the most fanciest words as they can come up with just to be annoying sometimes. And so oblique happens most of the time, but slanted is the same thing. You might see that. And the bottom line is, in order to do this, you need to actually divide, which honestly sounds easier than it is because polynomial division is annoying. Now, let's write it one more time. When do you do this? Because you only do this theoretically 1/3 of the problems. When do these happen? Nice. When the degree top is bigger than the bottom. Okay, so let's talk about how to divide polynomials. Let's say we have this question, 4x squared minus 3x plus 1 and x plus 4 is down there. Well, maybe we get lucky and this vertical asymptote of x plus 4 is actually a whole, and if we can just get rid of that whole thing altogether, then we'll just have a plain old line. Does this factor plus 4? No, this does not factor. So we actually have to do the divide. Now, there's two different ways to do big division. One of them is a shortcut. Okay, now this shortcut can be nice, and some people just don't like it at all. Okay, we're gonna talk about synthetic division. Have we ever done synthetic division before? Okay, synthetic division, when it works, when you do it right, synthetic division is great. Okay, I would recommend this is moments that you really kind of lock in because there's a couple different tricks to this. When you have synthetic division, you want to kind of draw a box set up in this way. This hopefully is kind of reminiscent a little bit. And maybe don't draw this part. This box has kind of, on your paper, you should draw it like that, where it has a top piece, a top portion and a bottom portion. And then we're going to basically be chopping it into columns as well. When we do synthetic division, we're only going to be using the coefficients. So for example, the coefficients here would be 4, -3, and 1. No x's make their way into synthetic. This is a very shortcut, cheeky kind of way to do it. Now, what do we want to divide by? And here's the piece. We want to divide by a root. Okay. When you go to divide by a root is the same thing as an x-intercept, a solution, a 0, a root, but it is not the same thing as a factor. So this number 4, or I said a root. I actually don't know if root is the right word to use, but we basically don't want to use that 4. We have to use the -4. Once you've set it equal to 0. You don't want to use factors. You want to be setting these equal. I'm not sure. I have in here root. I'm not sure if you can call that a root because it's the bottom equals 0, not the top. But anyways, we're going to divide by this, -4. When we go to do that, the process is bring down the first number and then multiply to get -16. This is a multiply. Step number 2 is then to add these two numbers to get -19. And then you're going to go back diagonally again, multiply. Now this is going to be a big number, 76, and then back here again, and you're going to add. That is synthetic division, and it works quite nice, and it's really easy, and you don't have to deal with any x's. It is a pattern. It is bring it down, multiply diagonally, add vertically. Multiply diagonally, add vertically. Once you get this, anytime you do divide, your number should be getting smaller. We started with x squared, and we divided by an x. So we lost that x. So a good way to do this is to think, I used to be x squared, but I lost one of my x's. So now this 4, which is my leading coefficient, it's not a 4x squared anymore. It's just a 4x. And where everything is going to be downgraded 1. This 19 is not a 19x anymore. It lost an x. It's just a plain old 19. And then this 77, which used to maybe be a constant, has to get downgraded even lower. And how do you get downgraded even lower than a constant? This is the remainder. Now, synthetic division, the first time you learn it, is good to check if things are factors. And so what remainder are we typically looking for? 0. A perfect divide with no junk left over. When we try to divide this, we're going to have junk left over. If you get 0, that means you were a perfect divide. That means you're a whole, because the bottom crossed out with the top perfectly with no leftover. So that means when we get this far, remainder is like your most likely case, okay? Maybe you want to take some notes. If 0, that means you're looking at a whole here. But most likely it's not going to be 0. Your slant asymptote is this piece, 4x minus 19, y equals. And what we do with the remainder is nothing. We just delete it. We just get rid of it. We just get rid of it because it kind of just evaporates itself. The remainder would be 77 out of x plus 4. And because that bottom has an x, that bottom could change. If that bottom became 10 million, 77 divided by 10 million would be basically nothing. 77 divided by negative 10 million would also be nothing. And so basically, because this bottom can grow and shrink, this fraction, we just don't care about it. So there you go. There's your slant asymptote. There's your oblique asymptote. Now, that's your synthetic division reminder. Here's your synthetic division question that's much faster. X squared minus 10 divided by x minus 3. Can you find me the slant asymptote? Up first, make your synthetic division little box. Up next, coefficients. What are the coefficients of the top function? 1 and 0 and negative 10. Here's the first kind of annoyance with synthetic division, is it can be very easy, or really with all polynomial division, you have to include that 0 because that's how many x's we have. We have 1x squared, 0 x's, and negative 10 constants. Out here, what number are we choosing to divide by? The 3, not the factor of negative 3, but the true. I'm just going to call it the root of 3. And then this process is easy. Bring down the 1, multiply 3, add 3, multiply 9, add negative 1. Writing the equation is also easy. That last number, who cares? Get rid of it. Downgrade, this would be x. Here we go. Y equals 1x plus 3. There is your oblique asymptote. Not a long process. The whole thing took us, I don't know, 30 seconds because I was kind of waiting on you guys to say whatever, but you guys could have done it even faster. Now, synthetic division runs into some problems, okay? We like synthetic division, but every question that we've seen so far has just a very small, beautiful denominator, and the reality is those small, beautiful denominators that you worked with when you did, math analysis or whenever you learned synthetic division, well, now we are in IBHO1, and we're not going to get such beautiful denominators all the time. So let's see a question here. 3x cubed plus 5x squared minus 6x plus 1. It's a cubed. And let's divide that by x squared plus 2x plus 1. So when I look at this, I think, okay, nice. The top is bigger. It is going to have an oblique asymptote. I see the bottom, and I think, you know what, actually, I can factor that. But do you know how to factor the top? No. So it's not even worth factoring the bottom unless we're looking for the vertical asymptotes. But for right now, I'm not going to be able to factor the top, so I'm not looking for holes. I just need to do division. And synthetic division doesn't work quite as well because we want to divide all of this bottom stuff, which is two things. It's your x plus 1 and your x plus 1, and we can't kind of separate them. So instead of doing synthetic division, we need to do regular division, regular polynomial division. So we're going to take this and we're going to write the whole thing. 3x cubed plus 5x squared minus 6x plus 1. And then over here, we're going to write the whole thing. X squared plus 2x plus 1. Now, here we go. If you needed to kind of do some jumping jacks or some warm-ups or something, how you do this division of polynomial is you want to turn this first number into this first number. Okay, focus on those first terms. How can you turn an x squared into a 3x cubed? What would you need to multiply it by?
3x.
You would need to multiply it by a 3 and an x. Then you're going to take that 3x and you're going to put it in the correct column. Does it go here with the x cubes? No. Does it go here with the 5x squares? No. It goes here. And then you are now going to distribute this number and put it underneath. And what should happen is everybody helped us specifically choose the 3x to specifically make 3x cubed. We chose this on purpose. We chose the 3 to turn 3 times 1 equals 3, and we chose the x so that x times x squared would be x cubed. And now these are the same. That's exactly what we're looking for. If that doesn't happen, you've messed up. Let's keep going. 6x squared. Let's go one more time. 3x. Now this column is just kind of empty for now, so just ignore that column. We didn't get that far, it's fine. And we're going to be subtracting these things to kind of get rid of them and to move them on. So let's do a subtraction. Now when you do subtraction, you got to subtract all the terms. So we're going to be subtracting 3x cubed, and we're going to be subtracting 6x squared. If you need to go through and kind of like distribute that negative, then do it. Don't mess that up. That's going to be 0. That's going to be negative x squared. That's going to be negative 9x. And that didn't happen, so it's just a 1. Okay? Up next, How do we turn this into this? -1. So we're going to put a -1 right here. And here's the nice part. We can just pretty much stop right there. Everything else that we would want to do would be worth figuring out our remainder, but we're not really caring about remainders when it comes to the oblique asymptote. And so this, which looks like y equals mx plus b, that is a good enough place to stop. Our oblique is at 3x minus 1. And maybe we put y equals, because it is a line. Come on, Mr. Collier, we need that y equals. Sorry about that. All right, we're going on. If you didn't quite finish that. (5x cubed plus 9x squared minus 6 over x squared plus 4x plus 4. Hey, that's the second time we came up with that denominator. Maybe I'm not as good as come up with random numbers as I think I am. All right, I'll help you set this up. Put the whole thing underneath. 5x cubed plus 9x squared. And we do want 0x minus 6. We do want that kind of placeholder thing. It's not really doing much, but it's given us room to kind of create that column to help us out. Out front is going to be x squared plus 4x plus 4. Okay, from here, we want to turn the first number into the first number. And how do we do that? Multiply it by, normally it's a pretty easy small thing. I'll let you guys do this and come up with the slant asymptote on your own. I'll give you 1 minute, maybe less, 30 seconds. You got it? I mean, it's those IB questions. So the reality is you would need to be prepared to graph it.
Without a calculator or just proportional with a calculator?
If you're doing this work, if you're graphing it with a calculator and all you need to do is graph it, then you probably don't need to do all this exactly. But if it says graph this equation and draw your asymptotes, or graph this exactly, including oblique asymptotes, then you'd want to go this far. But
So are we going to go over how to graph it without, like, by hand?
yeah, I mean, graphing it, you just take whatever line that we get. So let's do this one. I'm going to want to multiply by 5x and put that in the x's column. Then I'm going to want to distribute that and get 5x cubed. Nice, because these need to cross out and go away. Then I'm going to get 20x squared. Stop, please. 20x squared. And then I'm going to get 20x. And then I'm just going to have to bring this down. That's a 20. I'm going to add these up, and I'm going to get 29x squared plus 20x minus 6. Is that okay? Is that how we? What did I do? Subtract. I got freaking distracted by ugly thing. Subtract 20x squared and 20. Then subtract them. Good call. So that's negative 11x squared minus 20x minus 6. Is that better? multiply by negative 11. And then at that point, we can pretty much stop. So this is our slant asymptote, y equals. And if you were tasked with graphing this function, y equals 5x minus 11, here's negative 11, here's a gradient of 5, then you would want to do all your other stuff. It looks like this one has a vertical asymptote at negative 2, because this would be x plus 2, x plus 2. So negative 2, there's also an asymptote like that. This graph would look, this asymptote would keep going, this asymptote would keep going. This graph would look something like, this graph would look something like this. Now, if you had a graphing calculator, you'd already kind of know what it looked like, and you could just kind of sketch, unless it said, you know, make sure you state this. The homework doesn't have us graphing this. So
I was just wondering, it's like, I don't remember how, like, I can figure out that asymptotes do on that, just the graphing graph. How are those different forms?
yeah, like different shapes and stuff. Yeah. Okay, here's what we're gonna do. We're gonna do one last little question here. And we've been going for a while. I said it was a bit of a doozy for notes. It is what it is. We had an easy day last time you were here at least. So let's start with this. F of x, I'm gonna try to go quickly. All right, the reason I'm pushing you guys for this and we're going through this is because I was researching this topic and doing IB questions, and I ran into a question like this, and I went through it the first time, and then when I was about 80% of the way through, I realized, oh, this is a clever little question. And I just want to make sure that we don't panic when we see something like this. It says, find all asymptotes. Okay, find all asymptotes. Well, that's great. Which type do you want to start with? Vertical, horizontal, oblique? Vertical. And how do we find the vertical asymptote? Bottom equals 0, factor, you're all on the right track. Who can factor the bottom? Everybody. What do you get when you factor the bottom? X minus 7, x plus 4. And so what are the vertical asymptotes? X equals 7, x equals negative 4. Nice. Horizontal asymptotes. Compare the degrees. Who wins? Dang. Dang. Oblique time. And it's one of these big ones. We're not doing synthetic. We don't have the nice little beautiful thing. But at the same time, this is not really an insane process. We want to turn the first number into the first number. That's multiplying by 2x. We want to turn, or then we want to distribute 2x cubed minus 6x squared. Multiply that. Oof. At negative 56x. Then we want to subtract them. Change my signs because I got distracted and missed it last time. This is going to go away. This is going to be 5x squared. This is going to be 24x. Bring down the 16, but at the end of the day, who really cares? How do we turn the x squared into a 5x squared? Times 5. And you know what? It's good enough. Horizontal asymptote, none. Oblique, 2x plus 5. Now, I told you guys I wanted to do this question. Maybe I'm going too fast and you're catching up writing this, but just listen then. I was doing questions, working through them. This question, really, it's like, okay, there's not that much to it, not that much going on. We got our verticals, the horizontal was not there. We had to do the oblique, but the oblique, we're getting the hang of it. We're doing it pretty quick, not too bad. And then I thought, wait a second. This isn't quite right. What could we have messed up? The vertical asymptotes were the bottom equals 0. Yep. The horizontal asymptote, yep, we did that. Oblique, yep. What could have happened? Did you say hole? Yeah. What about a hole? Now, factoring this numerator is actually doable with Algebra 2 skills if you learn grouping, but some of them you won't be able to even group. And it might be some insane numerator that you can't really factor at all. These are problem areas, but we're not exactly sure if they are holes or not, holes or asymptotes. And the way we could check is divide them and see if you get a remainder or not. If you get 0 as a remainder, it's a perfect fit, which means it's a factor, which means it is a hole and not a vertical asymptote. So we need to go and do a little bit more work with the 2 vertical asymptotes in order to check if they are holes. Now the good news is that the vertical asymptotes are those nice little beautiful binomial pairs. And so we can use synthetic division if you want. Or you could go for the big division. If you just want to say, I'm locking into the full thing and I'm never going to do synthetic ever again, that's fine. But because these are nice, we can do synthetic here. 2, -1, -32, 16. I'll choose my root of 7, bring it down, that's 2. Multiply 14, add 13. Multiply, yuck, 91, add 59. 7 times 59, is that going to make 0? No. All right. So 7, what does that mean? Is 7 a vertical asymptote? Is 7 a hole? 7 is an asymptote. 7 is a problem. It does not divide perfect. 7, we can double down and feel good about 7. What about -4? So -4, the same exact thing. 2, -1, -32, 16. Bring it down. That's 2. That's -8, -9, 36. Already I can notice these numbers are closer together, which means there's a chance. That's going to be 4. That's going to be 16. -16. That's going to be 0. And boom. -4 is a perfect divide, which means it comes out as a perfect factor, which means it exists on the top and on the bottom, which means that this asymptote ended up being a hole. Now, none of that is mathematically hard to do. It's a little bit of a brain track, right? You have to really path for this question and really kind of be extensive and follow through a whole bunch of stuff. But just like we had a little bit of a legs day on Wednesday, we covered all of quadratics. We've worked hard today and we've covered rationals. I mean, there's not really a stone that we haven't turned here. I guess graphing, but again, as far as today goes, we're not doing graphing on the homework. So, all done.